Hello, everyone. We are doing a lesson today on electron orbitals, and you've learned a little bit about um, electrons existing on energy shells or energy levels, and it's a little bit more complicated than that, as you might guess. And so we're going to dive into these. These are different, you could think of them almost like subshells, okay, and we call them orbitals. So, what does that all mean? We know that Niels Bohr discovered that if you excite electrons, give them a little extra energy, they will pop up to a higher energy level, and then they eventually drop back down, relaxes, and it will give off that energy in the form of light, very specific wavelengths. Um, and so that led him to propose the shell model. So you already know about the orbitals from Bohr. You know that the first shell can hold 2 electrons, right? The first energy level can hold 2. You can see that on the periodic table. And then the second period, the second energy level can hold 8, and then 8, and then 18. But in reality, uh, it's actually that those energy levels have sublevels, and we call those orbitals. And we have a diagram here of those levels. So the first energy level has an orbital called an s orbital, and you can fit 2 electrons in an s orbital. And then the next energy level has a 2s orbital, and you can fit 2 electrons in there. And it has 2p orbitals, 3 of them, and each of those can hold 2 electrons. So you can have 6 electrons in the 2p orbitals. So how many can you fit in the second energy shell? Well, you can have 2 here and 6 here. That adds up to 8. Okay, and so we get this sense that it's a bit more complicated than we first learned back in Science 9 or Science 8. So atoms will all fill these orbitals from the lowest energy shell, 1s, upwards with electrons. So 1s has to be full before we put electrons in the 2s orbital. And so these orbitals, they have different structures, different geometries. And so the s orbitals look spherical, and the p orbitals look kind of like dumbbells. Okay, and there are 3 of them, and that's simply because they can be along an x-axis or a y-axis or a z-axis, like that. Okay, and then the d orbitals, look at those shapes. Isn't that awesome? And don't even get me started on the f orbitals. They get wild and crazy. So this is a diagram of the periodic table with the layout of the orbitals. And so we can do an electron configuration, and that's going to be a description of which orbitals have electrons and how many electrons are in each orbital. So if we think of helium, helium is way over here. The second atom, second element in the first row. Okay, the first row has 1s orbitals. Okay, there's one s orbital, an s orbital at level 1. And how many can fit in an orbital? 2. You can fit 2 electrons in an orbital. And so we can write out the electron configuration of helium as 1s2. That means there are 2 electrons in an s orbital at energy level 1. Okay, 1s2. What about beryllium? Beryllium is right over here. Okay, well, just a little peek here, we can see it's got 2 electrons in the 1s orbital and 2 electrons in the 2s orbitals, because here it is. Okay, and so we can write it out like this: 1s2, 2s2. That's not so hard. What about fluorine? Fluorine is way over here. And you can look at this diagram. It's going to be 1s2, 2s2, and then we move over here. These are the 2p orbitals. And we've got 2p, 1, 2, 3, 4, 5 for fluorine. So fluorine is going to be 1s2, 2s2, 2p5. Okay. Remember there are 3 p orbitals. 1, 2, 3. And each can fit 2 electrons, which means we have 6 possible elements here. Okay? And if we include the 2s orbitals, or electrons, that means there are 8 in that second row. Okay. So an electron configuration is a description of the orbitals. What about sulfur? Sulfur is right over here. That is going to be a little bit more complicated. So we've got 1s2, 2s2, 2p6, 3s2, and then 3p, 1, 2, 3, 4. Okay, so that's getting a little bit longer. And this is just for sulfur. So if we do something way down here, that's a lot of writing. So there is a way to do this a little bit shorthand, and that's by doing something called the core configuration. And core configuration just looks at the previous noble gas and then goes from there. Okay, so if we think of sulfur, we can backtrack to the previous noble gas. That would be this one. Okay, and then from here, just do the rest. Okay, so that noble gas here is neon. So we just write neon. And then neon, from there we get 3s2 and 3p, 1, 2, 3, 4. Okay, so we just kind of started here. Instead of writing 1s2, 2s2, 2p6, that is the electron configuration for neon. So let's just write neon in square brackets and then go from there. Okay, what about if we're doing rubidium? Again, that would be a lot of writing if we're doing the full electron configuration. But we can backtrack to this one. Okay, and then from there, this noble gas, it's just going to be 5s1. So this noble gas here is krypton. You can look on your periodic table, and then 5s1. Okay. What about krypton itself? Krypton is a noble gas. Can we short circuit this? Can we just be sneaky and just do square brackets krypton? Woo! Outsmarted the system. Sort of. No, actually we can't. Okay, we have to still backtrack to this noble gas over here and then go across. Okay, so that noble gas was argon. Argon is right above krypton. And then we do 4s2, 3d 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then 4p, 1, 2, 3, 4, 5, 6. Okay, so that's core notation. Okay. Now, that's how electron configuration works. But there's always exceptions. Am I right? So let's think of something like chromium. Chromium is argon and then 4s2, 3d4, but half-filled shells and filled shells, when it ends on a half-filled shell, that is more stable. Or a full shell, that is more stable. And you have an understanding of that because you know that the noble gases have full shells and they are more stable. So 4s2, 3d4, 3d 1, 2, 3, 4. It is almost half full. Okay, we've got a full one and one that is almost half full. this can actually become more stable if we go, let's move one of these electrons into here. Now this one's half full, and this one's half full. Okay, and so chromium will actually have 1 electron in the 4s orbital and 5 in the 3d orbitals. Okay, so 1, 2, 3, 4, 5, and now this is half full and that's half full. Okay, what about copper? Copper is 4s2, 3d9. Oh, that is so close to being full. This one is full, but this one is 1 away. Okay, but if we sneak one of these electrons into here, and actually we don't need to sneak it, copper does that for us. It is like that naturally. Now the 4s orbital is half full, 4s1, and the 3d orbital is full. Okay, so there are some exceptions, okay, where it's a little bit different than we would expect. Okay, and actually this helps to explain some of the behavior of the transition metals that are in the middle here. Okay, what about ions? Ions are atoms that will lose electrons or gain electrons. So negative ions have gained electrons. Okay, and so to write the electron configuration for ions, just add electrons to the last unfilled subshell, starting where the neutral atom left off. So this is oxygen, helium, and then 2s2, 2p4. But now we want to turn it into an ion. So it's going to gain 2 electrons. Where would those go? Well, it's going to become 2p6, right? It's going to fill up this orbital there. Okay, so here, this one is oxygen. This is O negative 2. What about Cl negative 1, chlorine ion? So this here is chlorine, but it's going to gain 1 electron. Where will that go? You guessed it. It's going to fill up the p orbital. Boom. 3s2, 3p6. Okay, so here's chlorine, neon, and then 3s2, 3p5, and it becomes neon 3s2, 3p6. Okay, hopefully that makes sense. But you ask, what about positive ions? Great question. So electrons are removed first from the outermost shell. Okay? And then if we need to remove more, we remove them in the following order. First from the p orbitals, then the s orbitals, and then the d orbitals. Okay. Potassium plus 1. We are going to remove 1 electron. From where? Well, from here. Okay. So what does that become? It becomes similar to argon, and we write that not by going square bracket argon. Nice try. Would be nice, but no, we'd go back to neon, and then 3s2, 3p6. That's not so bad. Tin. Tin 2 plus. What will that become? Where will it lose electrons? Well, it's going to lose these two. And so a tin ion, tin 2 plus ion becomes basically krypton 5s2, 4d10. And it's lost those two. Okay, so this is a SN2 plus ion. But tin can also become 4 plus. So how does that happen? You probably wondered that back in Science 9. Well, we can lose these two. Okay, we first remove them, remember, from the outermost shell. And then we're going to lose them from the p orbital, then the s, and then the d. So we're not taking them from here. We're first going to lose from this orbital. Okay, and so it becomes krypton 4d10. And that's why tin is a multivalent metal. It can lose some of the electrons in the 5s orbital. Okay, valence electrons. So you should remember that valence electrons are electrons in the outermost shell. But now that we know that shells are a little bit more complicated, it's important for us to think, okay, what are the valence electrons? Because the valence electrons are the ones that are involved with things like bonding. So omitting the core, the ones at the center, and any filled D shells or F shells. Okay, the rest would be valence shells or valence electrons. Okay, so aluminum is right here. How many valence electrons does it have? It has 3. Okay, 1, 2, 3. 3 outer electrons. Okay, we didn't take into consideration any D or F shells because the D ones are down here. F is down here. What about gallium? So gallium is right below it. Okay, gallium also has 3 valence electrons. Okay, 4s2. We can ignore the filled D subshell here, right? Ignore any D or F shells that are full. And then we've got this one is here, 4p1. So the 2 4s electrons and the 1 4p electron. Okay? So valence electrons. Trends in the table. Okay, this is the last part of this lesson. So there are trends that we're going to be discussing. There's a graph in the following slide that shows ionization energy for the first 86 elements on the periodic table. So what is ionization energy? It is the energy that is required to remove 1 electron from an atom. Okay? And so we're going to make some observations about the graph. Okay, so here's our graph. First observation. Okay, so we've got hydrogen, helium, lithium, etc. We're moving along the periodic table. Okay, what are these ones down here? These are the alkali metals. Lithium, sodium, potassium, rubidium, cesium. And you'll notice it takes very little energy to remove an electron from these elements. Okay, why? Well, because then they can become like the noble gases and have a full valence shell, right? So these ones very easily lose an electron to become a positive ion. What's something else we notice? I mean, these ones here, what are they? These are the noble gases. It takes a ton of energy to remove an electron from helium. That's why it doesn't naturally bond with other elements, because it's not likely to lose an electron. Okay, same with neon or argon, krypton. Okay, as you move across a row, okay, that's like doing this, right? We're going across that row in the periodic table, lithium, and you move across, so beryllium, boron, here we are, lithium, beryllium, boron, carbon. Okay, we're moving across all the way to neon. It requires more energy to remove an electron. Okay, even for the next period, the next row, sodium, etc. Okay. Next observation, as you move down a column, it requires less energy to remove an electron, just a little bit, right? Lithium, sodium's a tiny bit lower, potassium a little bit lower, rubidium a little bit lower. Okay, Here's helium, neon, right? So we're moving down the period of the noble gases, and it takes a little bit less energy to remove the electrons each time. Why? Well, we'll get to that, but think of that. Think of this. Where is the outermost electron for a helium atom? It's actually very close to the nucleus. Think of a Bohr model diagram of a nucleus of an helium atom, right? It's right there. Whereas neon, its valence electron is out here, and argon is out here, krypton, xenon, okay? And so removing this electron is easier because it's further away from that positive charge. So it takes less energy to move it. So xenon or radon, it's going to be easier to actually get those to become an ion. Hopefully that makes sense. Okay, so some trends that I'd like you to remember. As we move from left to right, you get decreasing metallic character. Okay, in fact, at the far side, we say they're non-metals. Okay, so strong metallic character, things like yeah, different metallic character decreases as you move from left to right. Increasing ionization energy. Okay, it takes more energy to remove electrons as you move across. We just saw that, right? Very easy to remove electrons from potassium, but gets harder as you go to calcium, scandium, etc. And here it's super hard. Increasing electronegativity. That is something we will get into more on another lesson, and that deals with its hunger for electrons. Okay, if it's going to bond with another atom and they're sharing electrons, if this one's very electronegative, it'll pull those electrons toward it more. So as you move from left to right, these ones are more electronegative. And decreasing size. It's kind of weird, but as you move across the periodic table, the atoms get smaller. Okay, scandium's a little bit smaller than calcium, even though it has more protons and more electrons. Why is that? Because even though you're adding more protons, okay, more stuff, and you'd think it would be getting bigger, more protons means a greater attraction for the electrons, and the electrons get pulled in a bit. Then you add another proton, so you go from scandium to titanium. Stronger attraction on those electrons pulls them in a bit more. Okay, what about as we move up the periodic table? Well, decreasing metallic character, okay, as you move up. Also, increasing ionization energy, right? The opposite then is true as well. As you move down, it's decreasing ionization energy. Takes less energy to pull an electron away from cesium than lithium. Why? Well, that outer electron from cesium is so far from the nucleus compared to lithium that it's easier to just pull it off. Okay? So if you move up to lithium, it's going to take more increased ionization energy. What else? Increasing electronegativity and decreasing size. Okay? All right. So you'll have to know those trends and also use that information for other types of problems we'll be solving. All right. We are going to do an example question together. It's number 48 from page 168. I think it would be helpful if we do that together because there will be other questions kind of like it. 48a, what happens to the distance between the nucleus and the outermost electrons when you go down a chemical family? Well, here's lithium. Think of the Bohr model diagram for lithium. It's going to look like that. Bohr model diagram for sodium looks like that. 2, 8, 1. Bohr model diagram for potassium. 2, 8, 8, 1. Okay? What is happening to the distance between the nucleus and the valence electrons, the outer electrons? The distance is getting bigger. The atoms are getting bigger. Okay? So 48A, the outermost electrons get further from the nucleus. B, what happens to the electrostatic attraction of the nucleus to an electron in the outermost shell going down a family? Okay, electrostatic, is just this attraction between positive and negative. So what's happening to the attraction of the positive nucleus to the electron and the outermost shell? Okay, think of the attraction between this nucleus and that electron compared to the attraction of this nucleus and that electron, or this nucleus and that electron. Okay, now there are competing things going on here. We know that the nucleus is becoming more positive, so that would mean stronger attraction, but there's another thing that's having a bigger role, and that is that these electrons are just further away from the nucleus. And so since the electrons are further from the nucleus, they're less attracted to the nucleus. Okay? The electrons are just further away, and so they're less attracted to the nucleus. Think if I had two magnets, if I hold them pretty far apart, okay, they hardly attract, but as soon as you get closer, they attract more. Okay, C, what happens to the ionization energy going down a family? Okay, going down a family. Now, we've got this. It increases as you go up a family, so it must decrease as you go down a family. But why? Well, think of our last answer. Since the electrons are further from the nucleus, it takes less energy to remove them. Therefore, ionization energy decreases. Okay? It's easier to remove an electron from cesium than it is from lithium, which is also why cesium reacts so strongly when you put it in water, because it loses the electrons so easily. Okay? So don't chuck your cesium in the pond, kids. It'll react very strongly. Okay. So these are the questions I would like you to do. The first ones deal with electron configuration, and then the last ones deal with questions like ionization energy. Go for it.